Welcome back, everyone. Today we're going to be talking about the idea of a limit. Limits are extremely important in calculus, in all of calculus, and today we're going to be getting our feet wet with the idea of what a limit is. Now, all of calculus is based on the idea of a limit. They're extremely important as they underline two of the most fundamental operations that you'll study in Calculus 1 and Calculus 2 if you continue on, and even Calculus 3, or vector calculus at Lehman. And those two fundamental operations are called the derivative, which we refer to as differentiating, and integration, or the integral. Now, derivatives, when we differentiate, they allow us to talk about the instantaneous rate of change of a function, or any function for that matter, that's differentiable. We will learn that there are some functions that will not be, where we will not be able to differentiate, and there's a lot of them. There's infinite many of them that we can actually differentiate on. This idea of differentiating will lead us to concepts such as velocity, acceleration, population growth rates, marginal cost, flow rates if you're into economics. And the integral will help us compute areas under curves, surface areas, and volumes. So when we say areas under curves, we're not talking about your basic area of a rectangle or a triangle or even a circle. We're talking about shapes that are not well defined like this one's. Now, this quick video will serve as an introduction to limits, and we'll begin talking about this average velocity problem. Well, suppose that you want to calculate your average velocity as you travel along a straight highway. If you pass milepost 100 at noon and milepost 130 at 12:30 p.m., you travel 30 miles in a half hour. For those of you who don't drive, the milepost just simply marks how far you've traveled or how long a highway is. Now, your average velocity over that interval, and when we say that interval, we mean the milepost 100 and the milepost 130 is going to be 30 miles, not 0.30, 30 miles divided by half an hour, and that will be equal to 60 miles per hour. You could check this. It's a simple calculation. You do 30 divided by 0.5. If you use a calculator, it's going to give you 60. Or you could turn the 0.5 into a fraction, and you'll have a complex fraction. And then you could use the keep, change, flip method, and you'll once again get the 60 miles per hour. Now that is your average speed. If you remember using the distance formula, you could do some manipulations to it to actually get this result as well. I mean, this is basically what we're using for this. Now, even though our average velocity may be 60 miles an hour, we are pretty much certain that we actually did not travel at 60 miles the whole way. Sometimes you have to speed up to, let's say, 65, 70. Sometimes you slow down to about 40 or even 50. Or even 30 if you have a delay or whatever. But we know for a fact that we did not travel exactly at 60 miles an hour between these two mileposts, because I did not say that we were using cruise control, for example. So the speedometer velocity that we see is varying from moment to moment. The limit will help us define this instantaneous rate of change as you move from one point to the next, from 1 second to the next one, from 1 mile to the next mile. That is what the limit would allow us to do. Now, let's look at this first example, which will elaborate on this idea of average speed. So let's say that a rock is launched vertically upwards from the ground with a speed of 96 feet per second. Supposed to be that. Now let's neglect a resistance so that our example is much easier. From physics, we have a nice formula that states the position of a rock or any object thrown after t seconds, and that's given by the function s of t equals negative 16 times t squared plus 96t. This is a plus, This is t. Now, the position S is measured in feet, with S equals 0 corresponding to the ground. Now, we're asked to find the velocity of the rock between each pair of times. So when t equals 1 and t equals 3, and between t equals 1 and t equals 2. Okay? Well, if we needed to find what the average velocity between these two positions is, well, what can we do? Well, first of all, let's talk about the positions. So let's first find out what the position of the rock is after 1 second, after 3 seconds, and after 2 seconds, before we even begin to compare what the average velocity will be. Okay, so if we wanted to find out